Alright, so welcome, and we're starting enzyme kinetics, which is super fun. Enzyme kinetics are very important for all of your grad school admissions tests if you're talking PCAT, DAT, MCAT. It's also very important to understand enzyme kinetics because pretty much everything that goes on in the body is regulated by some enzyme or some set of enzymes. And if you can understand conceptually what goes on when we're talking about all of the different values and numbers that refer to a specific enzyme, it'll be much easier later on to understand how things are working with drugs, with pathways, with all sorts of things. So to get started, we have this problem set, and in the first question you're going to be, and in the next couple of questions, you'll be exposed to all sorts of Ks, which are equilibrium constants, just like we've been seeing since Gen Chem 2. So we have a couple on the screen here. We're going to go through them. We have Km, Kd, Ks, Ki, Kcat, K1, K2, K negative 1. So we have a lot of these things. So we're just going to go through them and try to understand in English what each one of these is and how we're supposed to interact with it. What does each one of these letters and numbers tell us about a given enzyme catalyzed reaction? So let's see here. I'd like to start off with this this over here on the right side, which is your general sort of enzymatic reaction. So the first thing that happens is you have enzyme, some concentration of enzyme, and some concentration of substrate. They exist independently of one another, and they're going to come together. Okay, so this would be time 1, and this would be time 2. And at time 2, they're going to come together, and you're going to have an enzyme-substrate complex. So enzyme and substrate stick together, and you get a complex of the two things. At this point, the actual reaction has to take place. So whatever residues are catalyzing whatever motion of protons or functional groups or whatever's happening, this actually happens as the enzyme-substrate complex exists. Then they have to break apart to form enzyme and product. And each one of these steps has its own constant, and you'll see them described in certain ways. So in some places you'll have K1 and 2, sometimes you'll have A and B, sometimes you'll have different letters. But what I want to make very apparent before we go into any of these is that when you're doing your problem set or you're doing anything with enzyme kinetics, it's incumbent upon you to first look at what's actually happening and determine what the terminology is referring to. It probably won't be a problem for the course because we're all, we have the same professors and we have the same problem sets and exams. But when you go to other courses or the MCAT or whatever you're using this for, the terminology might not always be so uniform. So let's start with K1. K1 in this case, in general, refers to the reactants being enzyme and substrate, as we see here, and going to the enzyme substrate complex. So we could write K1 is equal to, so this would be the enzyme substrate complex, and this would be E, right, and S. So that would be one way of writing K1. And as you might imagine, K2 refers to enzyme substrate complex dissociating into enzyme and product. K2, I believe in your problem set, is referring to also it sort of encompasses the reaction that happens as the enzyme substrate complex forms product and goes to enzyme and product. So those are two ways of describing this reaction. Now let's go into some of these other values that you might be a little bit more familiar with after your first couple of lectures. So Km refers to the substrate concentration at 1/2 Vmax. This is a very important concept. It's very important to understand how Km works conceptually. And there's another way to calculate it, which you'll need for your problem set. And that is going to be that Km is also equal to K1 plus K2 all over K1. That'll give you Km. For the first question of your problem set, you'd use that. Now I want to think about Km conceptually. If Km is high, it means that at 1/2 of the maximum rate of enzymatic reaction, we have a high concentration of substrate, meaning free substrate, not bound. That means that the enzyme has a relatively low affinity for the substrate, which should tell you, it should tell you just that. It means there's a lot of enzyme in solution, not a lot of it is bound. So the enzyme isn't that good. It has a high Km. It's not that good in terms of binding and catalyzing the substrate to product reaction. If it's low, if Km is low, a lot of the substrate is bound, and that means that a lot of it is in the enzyme, ready to react, ready to form product. So low Km means good affinity, good enzyme for this reaction. And you'll see more of that later, and that should become kind of second nature to you by the end of this unit. Kd is a dissociation constant. So in specific, for enzyme reactions, if we look at Kd, let me change colors here. Kd will generally refer to the breakdown step here. So just the sorry. It'll be how likely something is to break apart. So it might refer to the Kd in a specific reaction, and it has to be given. It has to tell you what dissociation we're talking about. It could be that the enzyme substrate complex goes to enzyme and substrate, but it could also be that the enzyme product complex goes to enzyme plus product. So what I want you to take away from this is that Kd is dissociation constant in general. Ka is a dissociation constant. So when you see Kd, think about what dissociation are we talking about? Are we going from enzyme product to enzyme end product, enzyme substrate to enzyme, sorry, this is wrong, it should be this. Are we talking about enzyme substrate to enzyme and substrate, or are we talking about some completely other thing? Just remember, it is dissociation constant, so figure out what dissociation is going on. Next we have Ks. So Ks in English is affinity for substrate. Whose affinity? The enzyme. And we can also describe that in two different ways. This is how you'll do it for your problem set. You'll use k to the -1 or k sub -1 over k1. But conceptually, I'd like to talk about it for a second as substrate enzyme over enzyme substrate complex. This should be ringing bells. All of a sudden, we've just seen this. This is a dissociation constant. But now we have specified that this has to do with the substrate, so the enzyme substrate complex and the substrate, and we've called it affinity for substrate. Why do we do that? Let's think about it. If we have a very low Ks, and also, by the way, this is going to be kind of synonymous to Km in terms of function, but not in definition. So don't get confused there. Just try to get the bigger picture of what each thing is. It's all just terminology to describe what's actually going on. If you understand what actually goes on with enzymes, substrate, and products, this will all fall into place. So as far as Ks, think about it. If we have a high Ks, it means we have relatively small amount of enzyme substrate complex and relatively high amounts of substrate and enzyme. This means that it's more likely to fall apart and be free than it is to bind. This means low affinity. So high Km, low affinity. High Ks, also low affinity. If we have low Ks, this number is large, and these are relatively small, which means a lot of it has bound, so it has a high affinity. If you need to pause the video, go back, do whatever you need to do, try to understand that inverse correlation between Ks, Km, and affinity based on what exists in solution. Very important concept, fairly easy if you take the time to internalize it, but you need to have that definition down. And we'll do Ki real quick. So Ki is the same thing as Ks, but this is affinity for inhibitor. So once again, it's a dissociation constant. It would be enzyme substrate in the base, and enzyme inhibitor complex in the base, and enzyme and inhibitor separately in the numerator. So you can see, denominator and numerator. So you can think of it that way and try to figure out rationally why this is what it is, which is that if you have a high Ki, the inhibitor is more readily dissociated than it is bound, so it's not a very good inhibitor. It's not a very strong inhibitor, it's not very potent, however you want to put it. If your Ki is low, a lot of that inhibitor is bound, it's acted upon the enzyme, that's a pretty good inhibitor. I hope that makes sense. So there's a lot of Ks, and there's one more I want to go over as if that's not enough Ks, and that's going to be the K-cat, and I just want to go over that again, just conceptually. K-cat, or the equilibrium constant for catalysis, it refers to the overall rate. It also refers to, so this is also called the turnover number. Again, terminology tends to vary between scientists, between books. I've seen this as turnover number. But be meticulous about that. And in general, this will be the K of the rate determining step. Sorry about that. At any rate, generally the slowest step in an enzymatic reaction is the step wherein the actual reaction of the enzyme substrate complex takes place and it forms product. So K2 is generally the slower step, but no matter what's going on, you remember from Gen Chem that the rate determining step, the overall rate, is determined by the slowest step. So the rate determining step, the slowest step, is the K-cat. That K value is the K-cat. So what you would do is you would go find what's the slowest step. That's your K-cat. And that's what you'll use for the problem set. So I hope that that was beneficial. Sorry about the barking wolves, but there's not much I can do about that. If you have any questions, please feel free to email me. Consult your other TAs, your professors, and your course materials. And I look forward to studying enzyme kinetics with you guys in the workshop.